Let's dive into clustering. Clustering is one of the more fascinating parts of machine learning. And one of the reasons why it's so fascinating is that it discovers hidden labels and hidden patterns inside of data. So let's look at some key components of cluster analysis. Some key components are the distance, similarity, and dissimilarity functions, a loss function to evaluate clusters, also algorithms to optimize a loss function. But the goal of clustering is to find natural groupings in data. And this is really one of the forms of unsupervised machine learning. And often, though, the correct groupings are unknown, right? So there is no preconceived idea of what the right label is. And then also samples within a group should be more similar than samples in different groups. Now, how do you do this? Some of the ways you do this are with distance metrics. And here's an example, of a distance metric here. There's Hamming, Euclidean, cosine, right? There's lots of different metrics you can use, but in general, it's in multi-dimensional space. What is the relative distance between one item and another item? That's really the intuition. So let's go through here and look at one of these in action here. So if I go through here and I, again, import that data around the valuation of NBA teams, I can go ahead and I can write my own Euclidean distance. So if I import scikit-learn metrics Euclidean distance, I can actually go through here and say, grab a row, scale, and reshape to a 2D array. So here's what this function does. It, again, takes two things. Now, if I want to go through and I grab the first row, this is the first row of the data frame, here's the second row of the data frame, and then I want to use that Euclidean distance function, you can see here that I'm able to actually compare these two columns and find out how closely these two things are in a multidimensional space. Now, another one that we talked about earlier that's really, really important for clustering is that you have to scale the data first. So clusters have to be equally influenced by the features or dimensions. So one can't be in a certain scale and another one's in a different scale. And so you can do z-score standardization or standard score, which is the mean, subtract the mean, divide by standard deviation. You also can use the preprocessing in scikit-learn. And one thing to recommend as well is that you can actually use the scikit-learn pipeline feature to take the scaling and take the clustering and fit them in all one pass of the code. So if I go through here and I say from scikit-learn preprocessing, import standard scalar, next you'd want to do from scikit-learn.pipeline import make pipeline, and then the third step would be from scikit-learn.cluster import k-mean. So in a k-means algorithm that you're using scikit-learn on, really these are the three imports that should be in your code. Now, if we go through here and we load that data set here, again, the intuition is that they're different units. So here's a problem. We have to actually use our pipeline to rescale it. So let's go through here and let's use that make pipeline. Here we go. Here's an example. I use make pipeline and I put in the standard scalar and k-means, right? So it's in one line of code. I can both scale it and cluster it. And you can see here that it's relatively quick. Now, if I wanted to do it without scikit-learn, you can see it's much more code. You would go through here, first you'd scale it, then you'd fit it, and then you would actually apply all that at the same time. You can see here that depending on what the overhead is, this may be something you would want to benchmark in your code and see which one is going to be a quicker way to do it. Now let's dive into k-means in particular, which is one of the more popular clustering algorithms. One of the things to be aware of with k-means is that you can actually use diagnostics to determine whether there's a better way of doing the clustering. A few of them are elbow plots, silhouette analysis, and then also intercluster distance maps. So let's look at how that works with an elbow plot. If I go through here and I say yellow brick elbow plot, and I say from yellowbrick.cluster, import ke elbow visualizer, you can see that I make an instance of the model, and then I visualize all of the different iterations from 2 clusters all the way up to 12 clusters. Let's go ahead and do that. You can see there's a distortion score. And here really, this is when you see that elbow, right? This is the time it takes to converge, where the time it takes to converge, and also the distortion score. This should be the point where there's an elbow. And so this looks like this could be a good fit. Now, if I look at the scaled version though, this should be a little more accurate. You can see that this looks like potentially maybe this or here might be a better spot for the elbow. Let's go ahead and do an elbow plot from scratch here so you can see what this looks like. I would import matplotlib, and then I would look at all the different distortions, and I would plot how each one is able to visually look on a diagram. And you can see this is a little cleaner, that right here I have an elbow here of 3 different clusters. And it's always going to be a little bit of a gray area. Like you could say, well, maybe that's the elbow or maybe that's the elbow. But this one looks like it's, at least right in the middle, where 3 different clusters are probably the best choice for this particular data set. Now, if I go through here again and I want to look at a reference data set, this is a great way to get the intuition behind it, is you can import scikit-learn data sets, make blobs, which create synthetic clusters. And then I can go through and I can create this synthetic data set with 8 random clusters. And then if I want to look at this and verify, I can see that Yellowbrick should give me that number. And it does. In fact, it shows me that this is the elbow point that I want to pick here. And I know that it should be a total of 8 random clusters with 12 features, right? So this is another good way to really get a feel for elbow plot, is make a synthetic data set and then plot it with an elbow plot to verify that you really do understand how it works. There's another diagnostic method you can use with k-means called silhouette analysis. Let's go through and see how that works. So the silhouette visualizer, it displays the silhouette coefficient for each sample on a per cluster basis. What this means is that you can visualize which clusters are dense and which ones are not, and this really can tell you if there's an imbalance in the clusters. So if I go through here and I say from yellowbrick.cluster import silhouette visualizer, you can see here that this silhouette visualizer, I feed it 3 different clusters here, and you can see that it's a little bit shy, that it would be ideal if this cluster was past this silhouette line. And also you can see that these are relatively similar in size, but this cluster is very, very tiny, right? So this is just another diagnostic tool you can use. Now again, if I wanted to do that from myself without using the Yellowbrick library, I go through here and I do my k-means cluster, run that, and then I can just use matplotlib, and I can actually iterate through and make a from scratch silhouette plot. If we go ahead and we do that, you can see it looks very similar, right? I have a cluster here, and this one's a little bit shy. So there's something going on here where there's that 3rd cluster is a little bit iffy. So again, if I go through here and I look at a reference plot, that's a great way to make sure you understand how these diagnostics work. Is again, I make 8 blobs, and then I look at potentially an incorrect cluster selection here, right? So you can see again, this one's too shy. We know that in this case, there's not enough. All of the clusters don't get over that silhouette line. So if I go through here and I fix that though, you can see that now they're all basically up at that silhouette line. Now, one more diagnostic tool to use is the intercluster distance maps, and Yellowbrick also has a solution for that. The way you do that is you say from Yellowbrick cluster import intercluster distance. That's this example right here. And then you instantiate it. In this case, we'll give it 3 different clusters, and then I can transform that data and see what's the distance between the different clusters. And you can see, really on a multi-dimensional time frame, what is actually happening in my clusters. Now, if I want to do a Yellowbrick intercluster distance map reference plot again, you could pick, in this case, 12 blobs. I go through here and it's going to show me that they're all equally distanced apart, right? So there's a very uniform distribution of clustering. Now let's talk about some real-world k-means computational challenges. One of the problems with k-means is that it's going to perform differently on multi-core machines than a single-core machine, and also disk I/O could be a factor as well. So let's go through here and let's look at 25 k-means clustering algorithm operations here, right? So let's just imagine you're clustering many different data sets in your company. Well, how would you do that? Well, you could write a function here that just says do k-means, and then you could in serial run 25 iterations of this, right? So imagine this is 25 different data sets you want to cluster on. Well, each one is going to separately run, and so it's going to take the total time to do 25 clustering runs will be, 25, the sum of those 25 runs. So here we go. We can see that it's going through, and it's each one of them, it's taking about a half a second or so to run. So it took about 20 seconds. Now, what happens if I run this in parallel using the multiprocessing library in Python? Well, to do that, I would say import multiprocessing, and I look at the CPU count, and you can see this actually is a multi-core instance, this Colab notebook I'm using. So I can actually expect there be some parallelization that I can use. So what I do is I say from multiprocessing import pool, and then I take this same function that I had before and I run it in parallel by using the pool. So I say with pool, so spawn 10 different processes, and then map each of those functions onto those 10 processes. And so now it's going to do these in parallel. So at first, one thing to point out whenever you're parallelizing code like this is there's going to be, again, there's no free lunch. So there's going to be a fixed amount of time that the parallelization library is going to require to get things started. And you can see that all these have like this, a penalty of 5 seconds here. And the wall time that it took to finish this was a total of 16 seconds. So if I look over here and I look at my previous one, it's slightly faster. It's only a second faster because, again, of that fixed lookup time. But if we had, let's say, a larger data set, then that fixed lookup time would be less important in relative terms. Now let's also talk about how you could use do parallel k-means using Cloud9. So you could also use, let's say, a cloud provider and actually open up their cloud environment and do parallel k-means. Another example is you could go through and you could use something like SageMaker, which has parallel k-means clustering that's at your disposal. AWS Batch, you could run a job in AWS Batch. You could use EMR or Spark, and you could do distributed clustering that way, or you could spin up your own spot instances in AWS, and you could go through and train it that way. So let's shift gears here. Now that we've understood the complexity of k-means and how to reason about the runtime, what if we wanted to write a k-means algorithm completely from scratch? Well, I'm going to go ahead and copy some code from one of the other Pearson authors here, and he has a great video that kind of walks you through some of these concepts. His name's Raymond Hedinger, and you should definitely check out his video. So I just took some of his code and slightly modified it for our example. So here's an example of some pseudocode before we get into the actual code from Stanford Computer Science Department. You can see that you start out with k-means here. You initialize the centroids randomly, and then here's some bookkeeping here to just keep track of some state variables. And then you say, basically, run the k-means algorithm until you assign all the centroids, and then you then write a stop function here, and this stop function says, as long as I haven't reached my max iterations, go ahead and keep going, go ahead and get the label, go ahead and get the centroid, and then that's it in action. So how would I actually use that? Well, here's an example of 3 different vectors, and I want to calculate the distance between those, right? And then I want to calculate the distance between all 5 vectors. Here we go, right? So it's that real concept of Euclidean distance is really the intuition there. So now let's go ahead and actually write it out without doing pseudocode. So I'm going to start here and look at this example. So for every I set and for each J set, I'm going to go through and I'm going to figure out what the centroids are. So these are the functions that we're going to need to write. We're going to need to write a mean function. We're going to need to write a dist function. We're going to need to write an assign data function, and we're going to need to write a k-means function. So what I do is I import random, I import math, import fsum, square root. From statistics, I import mean. From collections, I import default dict. And then from functools, import partial. So here's an example here of this core k-means algorithm. First, I do a transpose. And what this does is it's going to swap rows with columns. And then I'm going to find the distance. So this is the multi-dimensional Euclidean distance, right? This is very similar to what I just showed. and then I'm going to assign the data. So I'm going to assign the data to the closest centroid, and I'm going to use a default dict for that, right? So only a few lines of code to assign the data, and then I'm going to compute the centroid of each group. And then here's the actual k-means algorithm itself, is I basically say for every iteration, go through and get the label and get the centroids. Here we go. And now if I want to test this out, I can actually take 6 three-dimensional points here. Here they are. And I go ahead and I take those and I run this from scratch algorithm. How does that work? Here we go. Let's go ahead and import random here. I believe this needs to be run. There we go. This needs to be run. Okay, so if we go ahead and we run this, you can see that it took about 2 minutes here, and I can actually plot out what the cluster centers are. So how does this work? And if I look at the assignments here, you can see where each one of these is actually assigned, which cluster, or where the center of the cluster is. Now, that's some code that we did completely from scratch, and again, thanks to Raymond Hedinger, and you can watch his video that really he gets into this in more detail. So now let's compare this, and let's look at how to do it ourselves using scikit-learn. So if I go to scikit-learn cluster here and import k-means, and I say import numpy as np, let's take that exact same algorithm here, and you can see that it's actually slower because I have to pay for all that overhead. And if I go ahead and I print the clusters, they look identical, right? And so this is a great intuition here, is whenever you want to understand an algorithm, sometimes if you write it yourself, you can get a much better feel of how it works. Now finally, let's wrap this up and let's do a quick sanity check. What I'm going to do is I'm going to go through here and I'm going to take this nested sum, and I'm going to basically go through and assert that both versions are equal, and I assert that the nested sum is equal to centroids are also equal to from the scratch version, so we can see that they're both actually similar. Now let's go ahead and visualize this k-means. Let's kind of wrap this up by looking at how we can actually look at some visualization techniques. In order to do that, again, I use my make pipeline here. I fit it, I put these labels which come back here, and I put those labels onto my data frame so that I can actually do something with this clustered algorithm. Here we go. Now let's go ahead and make a faceted plot. So one of the things that is really important to reason about with k-means clustering and clustering in general is that you can think of, and here's an example of an MBA data set, is that each of these facets here are clusters. And I'm able to label each of those facets and get some unique information about my data set. In this example, you can see this is called the best players in the NBA. These are the biggest players in the NBA. These are the ball handlers in the NBA. And so it's really that combination of clustering plus the labeling of the data that really gives you the power of unsupervised machine learning. So here's an example. If I wanted to go through and I wanted to do a binary value with clusters, you can see that I'm able to split out the Eastern Conference or the Western Conference, and I have these 3 clusters here. And you can see they're very uniquely separated, right? You can see here, this is how good a team is, right? The higher the ELO is, and this is the valuation. You can see that in the Eastern Conference here, it's very cleanly broken apart, and here's another section, and then here's another section. So really, really good visualization. Let's look at a different plot now, which is a faceted plot, and this one is going to have a continuous color output. And what this is going to show us is the darker the red, the more the valuation of the homes are in the region. So you can see here that even though I have, here's my cluster 0, here's my cluster 1, here's my cluster 2, you can see that this cluster, where the very dark red are, these are actually teams that have very high valuations of homes in their area. And you can see over here how light this is. These home prices are much lighter in this cluster 2, and you can see cluster 3 has got a combination of both. So really these data visualization techniques, when they're combined with clustering, really expose unique ways of looking at data. Now, if I go through here and I want to write out those cluster assignments as well, this is important to know. You could just say to CSV, it's going to dump it out, and now you actually have a permanent history. Let's wrap this up by looking at a 3D plot as well. So 3D plots plus clustering really go very well together. I'm going to enable Plotly inside of Colab Notebook, and here's how I do that. And then I'm going to, again, import Plotly offline. And then I'm going to put these basically these three different dimensions together. I'm going to put the valuation, the ELO, the median home price, and then I'm going to go through and I'm going to look at this cluster, and you can see again how this is a great way to visualize data by looking at it in a three-dimensional view, and then actually using these different visualization techniques to actually really explore and learn about that data set. Okay, let's also talk a little bit about things like Google Data Studio, for example. That's another good example of a tool that you could use to do data visualization. Here's an example of a data set that I've done recently that uses that. So what I did here is I took some clustered bike trip data, and I'm able to actually identify there's 4 different clusters here, and then I map these features. I map the distance from the city center, I map the duration, and I map the bike count and the number of trips. And you can see that actually it really exposes some really unique patterns with this bike trip data. One of them is that this is a cluster where it's really not that far away from the city. It's like a modern, like maybe a medium amount of distance. And the duration is also like, not the farthest duration. And there's actually, maybe a lower amount of trips, but there's a lot of frequent trips. So maybe a conclusion you can make here is that these are all people that are making like commuter trips, right? They're coming back and forth, and they're taking a lot of really frequent trips. Now, if you look at this cluster where here's the duration, these are maybe people that are coming from a far distance away, and they're going on very long trips to the city. And there's a lot of actual bikes that are doing this, but the trips are very low because of how long the distance is, right? So this again shows us how when you visualize the cluster, you can get a great feel for what's happening with the data, and it's a part of your exploratory data analysis. And this is just yet another tool you can use is the Google Data Studio. Let's also talk about another kind of clustering. One of them is hierarchical clustering. So with hierarchical clustering, it's a good approach for fast and high quality document clustering algorithms to play a role in, let's say, navigating through information. And also clustering algorithms could build out meaningful hierarchies out of a large collection of documents. And so it's a way of really visualizing document-based data. Now let's go ahead and look at how we would code that up. So I could go through here and I could take that same k-means approach here and compare it with hierarchical. And I use from scikit-learn agglomerative clustering. And I look at both approaches and I can visualize how they look. You can see that in this particular example, you have a much cleaner break of the data, and this is more clustered together with the hierarchical. So in this case, the k-means clustering looks like a better approach for our data. And finally, just the last thing to wrap up with is if you want to do this on your own, another approach outside of k-means clustering is you can use BigQuery. BigQuery now has k-means clustering as well, and then you could take that and you could move it back into, let's say, that Google Data Studio approach as well.